Hello students. Dear students, so we are going to learn chemical reactions of ethers. Dear students, please subscribe my channel Venus Academy if you are not yet subscribed, and don't forget to click on like button and bell button. Let us see the chemical reactions of ethers. So what are the common reactions it come across is the bond which is present in ethers is R, O and R. And the cleavage of this one chemical reaction is cleavage of oxygen and carbon bond. What is this reaction? It is nothing but de-etherification, or if it is commonly if it is methyl group, then if it is phenyl group, then it is known as demethylation of ethers or demethylation reaction. Then how to do? Yes students, so demethylation takes place under drastic reaction conditions. Drastic reaction conditions means high concentrated hydroiodic acid or HBr or HCl at high temperature, it is going to give ROH plus R iodide. If I use iodide, and the demethylation or the de-etherification capacity is HI is going to be very high, means it easily cleaves this bond, whereas HBr is better than HCl. However, the usual method is using hydroiodic acid HI. At high temperatures, it is going to cleave the ethers, right? So, which ether is going to be cleaved? For example, this is the ether. Which side is going to be out? So when I add HI, what is going to happen? And another example, if I take simple CH3 and CH2O CH3. So if I take this methoxyethane as an ether and do the reaction with HI, what I am going to do? The first step is, since it is ether is going to have lone pair of electrons, it is positively charged and this is negatively charged, and it takes a proton to give the intermediate of this CH3 CH2O, and CH3 is here hydrogen has come. So in this case the methyl group is very easy or unhindered. This side CH2 CH3 and this is having positive charge. So what is going to happen? This iodide molecule entering onto this carbon or this carbon, which is very easy to enter this side or this side. So this carbon is hindered, right? So this carbon taking up by this carbon is very tough compared to this. So easily it forms bond with this, right? So this is going to out as methyl iodide. And here it is going to like this plus, and this is OH, and the remaining is CH2 CH3. That means the bulkier group, whatever the ether you take, bulkier group is going out as alcohol, and the smaller the molecule, the smallest part, the smaller alkyl group or smaller alkyl group is going out as iodide. However, if I use excess of HI, even this ethanol, if I use excess of iodide, hydroiodic acid, it takes a proton and it is going to form CH2 CH3 and OH is already there and another iodide. And this also at this stage, just now what I said, at this stage this iodide enters into this to give CH3 CH2 iodide. Yes. So what is going to form from this methyl and ethyl ether, methoxyether? The products are, these are the products, methyl iodide and ethanol. Then the question is here. So just guess the products from this reaction. Yes, you can say that since it is a bulky group, in this example what I said, bulky group, it is going to break here. But it is not so. Not so. Because this case it is a primary carbon. But this carbon is tertiary carbon. What is going to happen? No doubt it is going to form this. At this stage, O, hydrogen is here, methyl group, and this is a positively charged, and this is methyl and methyl. Yes. So is it possible tertiary compounds undergoes SN2 or SN1 substitution? SN1, right? So SN1 substitution takes place. So at this stage, what is going to happen? It will be easy to lose this and to form tertiary carbocation, which is stable carbocation, right? And the remaining is methanol is this side, OH. And this tertiary carbocation may undergo elimination, right, to give propene, 2-methyl propene. Yes, students? So this is how demethylation takes place. However, to simplify, let us take one aryl methyl ether and you will enjoy the demethylation reaction. Yes, students. Let us take one aryl methyl ether. What you will enjoy? This is OCH3. And let us take one more example, OCH2. This benzyl methyl ether. And when I add HI here, what is the product? When I add HI and heating, what is the product here? Yes? So guess, is it easy to break this bond? No. So just rule out. This bond breakage is not going to take place. This bond breakage is not going to take place. Then what is left over? The methyl group. This is positive and negative. It takes up this and it is going to form oxonium ion. And iodide part will be there, iodide minus and O minus, O positive. Now what is going to happen? This comes here and this takes a proton to give phenol. So the demethylation reaction is very important, students, in synthetic organic chemistry, protection and deprotection. So demethylation takes place to give phenol. And the leftover other part is going to be iodide. Yes? So this is phenol and iodide comes out. When it comes to this, so is it going to break here, here or here? What is your choice? It is very simple, students. It is positive and negative. Let's just protonate this oxygen to give, this is the intermediate, O, hydrogen and CH2. In this example it is CH3. Just write it as phenyl group instead of writing benzene B group. So I can write it as phenyl group. So what it can follow? Yes, it is easy to enter iodide from this side and loses this, and I am going to get phenol, here also phenyl. So benzyl ethers are also common protecting groups. Phenyl, CH2, iodide. Yes, students? So this is how demethylation. The method is de-etherification or demethylation. or this is de-benzylation. D spelling is important. Benzyl, ZY, not ZOY. Benzylation, de-benzylation. So this is benzyl group. So de-benzylation can be done using concentrated HI or HBr HCl under heating reaction conditions to give alcohol phenols. Yes, so this is one of the methods of protecting this phenol group. You will learn in higher classes or during research, right? So benzyl group can be deprotected using HI. Yes, friends. So these are one of the chemical reactions. The very important chemical reactions of ethers are aromatic electrophilic substitution reactions. Let us take aromatic electrophilic substitution reactions. So the name itself says this aromatic ring. That means the starting material of the ether must have aromatic ring. So I will stick on to this anisole. The easiest or the best examples to be learned is anisole. The name is anisole. So anisole is methoxybenzene IUPAC name, or methoxybenzene or methyl ether of phenol. So this example, I will take this example and I am going to get this, explain this aromatic electrophilic substitution reaction. And before going into deep, so what is the orientation of this methoxy group? Methoxy group orients the incoming electrophile to ortho or para directing group. That means this methoxy group directs the incoming electrophile to ortho. This is ortho position. This is also ortho position, either of these two sides, and this is para position, right? So this methoxy group or ethers are ortho-para directing groups, similar to phenol. So ethers are ortho-para directing group. Why? You can write the resonance structures to learn how it is going to direct this. For example, methoxy. So it undergoes resonance to form anion. Carbanion forms at ortho position, and the electrophile is electron deficient compound. It loves electron, so it forms electron dense carbanion at ortho position. Yes, students. Then if I do write further resonance structures, and it forms resonance structure or carbanion at para position, and I can write further. So this is, and another ortho position we are going to have carbanion, and the oxane is all these resonance structures. It is tightly attached to this sp2 carbon, and it is oxonium ion. Now it will be back to this, where it is going to have methoxy ether. This is a double bond, and double bond. So these two are same, isn't it? So these two are resonance structures. So because of these resonance structures, what are the positions it is having? Carbanion at ortho, and this is para, and this is ortho. So it is getting carbanion at ortho and para positions during its resonance structure. So aromatic electrophilic substitution in ethers takes place at ortho and para positions. Let us take one example and see. Yes, So the usual electrophilic aromatic substitution is nitration. Let us take nitration. Same, take the anisole as starting material. And what is the nitrating mixture? Yes, sulfuric acid, concentrated sulfuric acid, it should be 2 moles, 2 equivalents are 2 moles, and the concentrated HNO3. This is nitrating mixture. These two is known as nitrating mixture. Please remember like this, nitrating mixture. This nitrating mixture generates NO2, electrophile. That I am going to give the mechanism. Electrophile of NO2, and it is going to nitrate or nitration takes place at 2 positions. What are the 2 positions? This is para plus this is ortho. Do you have any guess which one is going to be more or which is going to be major product among these two? This is para, this is ortho, right? Which is going to be major product or major product? Para position product is a major product, whereas ortho is minor product. Means the yields, if I get 100 grams of this mixture product, in that it is going to be about 90 grams of para and about 10 grams of this meta. Why? Because this group is already bulky, it is bulky group, and this carbon to enter this electrophile at this position, it is repels. So the incoming nitro group also is very big group, right? This big group entering at ortho position is not going to take place that easily. That is why the para is major. Most of the case in electrophilic substitution reactions of aromatic compounds, para product is going to be major. It is a thumb rule. Just remember, it is generalized rule. Most of the cases. So blindly if someone asks, para is going to be major, right? So para is going to be major if it is ortho-para directing group. And what is the mechanism? Yes, in all electrophilic aromatic substitutions there will be 3 steps. The first step is generation of electrophile. What is the next step? Second step is formation of carbocation or sigma complex. This is the second step. I am writing a mechanism step. The third step is removal of hydrogen from the sigma complex. So in this case, what I am using sulfuric acid. Let me write sulfuric acid. This is sulfuric acid and HNO3. Right? HNO3. So in this case, sulfuric acid is going to act as acid and this HNO3 is going to act as base, or it takes a proton from sulfuric acid to give HSO3 minus plus this is H positive charge hydrogen from this sulfuric acid has come and NO minus. This loses water molecule and gives the electrophile. This is NO2, or I can write NO2 electrophile. This electrophile now it is floating in the reaction mixture. What is there in benzene? Yes, we have this is anisole plus this NO2 is floating. It is there in the reaction mixture it simply takes up this lone pair electron, and let me write at ortho's position, and this is nitro, it's attached here, hydrogen is here, already one hydrogen, methoxy undisturbed, and this is double bond, and here carbocation. And this resonance structures, if I go on right, it goes out here, positive charge forms here, positive charge forms here, and then comes here, here it is going to form, here it is going to form. So the overall compound what I am going to get upon resonance structures, so this is the sigma complex, I can write it as like this. The positive charge is resonating in benzene ring, and this methoxy is there, and hydrogen is there, and electrophile in this NO2. This is a common mechanism, students, even for your Friedel reaction also. Right? Now the third step is, it is removal of hydrogen. To give, it is going to give, in this case, ortho, OCS3 and nitro. And same way you can write the para product also. Yes, students. So usually 3 steps I have been explaining in all chapters, but since if you are the first time viewer of this lecture, then don't confuse. So the electrophilic aromatic substitution consists of 3 stages or 3 steps, where generation of electrophile, formation of carbocation or sigma complex, or removal of hydrogen. This is how it undergoes nitration. Now you are clear about nitration. Let us see bromination and Friedel-Crafts reaction. Yes, students. So bromination and Friedel-Crafts reaction also is aromatic electrophilic substitution reaction. It also follows 3-step mechanism. Sorry. Yes. So bromination. Usually bromination requires Lewis acid, bromine plus Lewis acid, for the generation of bromine electrophile. But this ether or anisole or ethers are highly activating groups, so it doesn't require any ferric bromide type. For example, to generate electrophile bromine, if I give, to generate electrophile ferric bromide is usually used for the aromatic bromination, where it forms bromine electrophile, then ferric bromide Br4 minus. So this is a usual pattern, but it is highly activating group. So in this case, ferric bromide is not required. Not required. Simply take bromine in acetic acid. Usually we will get in acetic acid, bromine in acetic acid. We will get as a solution bromine in acetic acid, and this is going to form, bromination will take place. Bromination is going to take place at para bromo compound and ortho bromo compound. Which is major in this case? Which is major? Same story. So the para is major. This is ortho. Para is major product, whereas this ortho is minor. The same thing is, bromine is a big atom or molecule, where this is also very big methoxy group, and entering at ortho position is very tough or hindered. Yes, so hindered. So this major para position is very easy to approach this benzene ring. So that is why it gives major product. Same thing, if it forms 100 grams, it is going to be 90 grams or 90% of this para, and this is 10% of ortho. So this is how bromination takes place. It can be chlorination, it can be iodination also. Right? Iodination, it follows different mechanism, but bromination and chlorination you can do in this way. Right? Let us take very important chemical reaction of ethers, aryl alkyl ethers is Friedel-Crafts reaction. Yes, students. So Friedel-Crafts Friedel-Crafts reaction. What is this reaction? It is aromatic electrophilic substitution reaction. It can be asked in some entrance texts that what is the type of reaction of Friedel-Crafts alkylation reaction? Yes, it is also aromatic electrophilic substitution reaction. Yes, so this aromatic electrophilic substitution can be written as right, like this also, right? So let us take alkylation. What is alkylation? Let us take anisole OCH3 plus alkyl halide. It can be bromide, chloride or iodide. So under Friedel-Crafts alkylation, iodides or for example if I take methyl iodide gives better yields compared to methyl bromide compared to methyl chloride. So which one I am going to use? Let me use methyl bromide. Yes, and in presence of anhydrous aluminium chloride, the solvent is, usual solvent is carbon disulfide. Yes, its boiling point is around 50 degrees centigrade. Take this carbon disulfide and do the alkylation of anisole. You are going to get the mixture of compounds are this orthomethyl anisole plus paramethyl. And what is the ratio of these two? Yes. So usually all the times it may not be 90-10%, but the usual pattern is para is going to be major. Para and this is ortho. Yes. So blindly you can say it is major. It is exactly not 90-10% and it is minor. Yes, students. Then another type of reaction, it undergoes Friedel-Crafts acylation. Acylation, what are the starting materials? So if I take same anisole and react it with this acyl group. What is acyl group? CH3 COCl, acetyl chloride. The common name is acetyl chloride. I can use acetyl chloride. The different textbooks giving separate the different names, but I am teaching the common names are the names used in research papers. Yes, so remember like this, acetyl chloride. Yes, acetyl chloride can be used in presence of anhydrous aluminium chloride. What is the compound I am going to get? Acetophenone. Acetophenone. Yes, students. So acetophenones we are going to get. This acetophenone is paramethoxy acetophenone and orthomethoxy acetophenone. And what is the ratio? Again, write it as this is major and this is minor. And another key point to teach make you know is, so how to separate these two compounds. Dear students, it is very simple. Write down steam distillation. Steam distillation separates these compounds. How? So this acetophenone is having oxygen, this is also oxygen, and it is very near to each other, so it is going to have some minimum hydrogen bonding. So orthoanisole or orthoacetophenone, methoxyacetophenone is going to low boiling point, and this is para is going to be high boiling point. And the first this low boiling point compound distills out with steam, whereas this high boiling points are compound distills out later. And one more thing, why this para is going to be high boiling point? Because of this linear structure, I can say. So in a crystal or in a molecule, if it is a liquid, it is going to be tightly packed. So it is symmetric. I can write like this, right? CS3. So it is straight chain, straight, some linear structure. Whereas this is it is different structure, right? So it is not going to tightly packed. It is going to be tightly packed, so high boiling point. Dear students, so this is how ethers undergoes Friedel-Crafts reaction. Yes, so dear students, I hope you enjoyed this topic. Please subscribe my channel Venus Academy if you are not yet subscribed, and don't forget to click on like button and bell button. We will meet again with a new topic. Till then, bye. Sayonara. All the best. Arigato gozaimasu. Thank you very much. Bye students.